Good evening to everybody. My name remains Timothy. This night, we want to continue our lecture and training on deep learning with Python, including practical illustrations. Today is May 14th, 2024, and it's our day 12 of this lecture. So let me introduce our instructor to you in person of Salah Ayobami Mohammed. Ayobami, please take over and the charge as expected. Thank you.
Okay, good evening, everyone. Good day, everyone. So we are going to continue from where we stopped yesterday. So we looked at how to feed a deep neural network yesterday. So and we talked about the roadmap that we're going to follow. So now we are already in the architecture aspect. So what we're going to do is that we're going to talk about one particular architecture. So we're going to look at CNN as convolutional neural networks. So we're going to explain what it is, how it operates, the the tactics behind it, what it looks like, and how what happens in the CNN architecture when we feed it with a feature. It can be an image, a sound, or anything, and what happens during the process when that feature is being turned into a a map, something that goes into the architecture, then gives us an output. So we're going to look at that. So we're going to learn about what computer vision is because basically CNN is used for computer vision projects. I'm going to talk about convolutional neural networks and CNN layers. And so now, what is computer vision? We have been hearing a lot about computer vision. So it's a very popular field of AI, and it's a disciplinary scientific field. And what computer vision is about is enabling computers to understand from digital images or videos and taking action based on the information obtained from visual inputs. That's what computer vision is. And data are captured from cameras or generated in computers. And another thing about computer vision is actually helps us do modeling of image processing using machine learning techniques, and also applying machine learning to recognize patterns from images or frames. And what actions to do is actually something that is generic with computer vision. Either it distinguish between objects or classify them, and so on and so forth. It's either we have distinguishing, classification, we have segmentation, and some other things that has to do with computer vision. So now, still on computer vision, one thing there is by utilizing computer vision algorithms, we can identify objects. An example of that is this. Now, if you look at this, these are bounding boxes. What I call bounding box is this yellowish rectangle. You can see that it's been placed on each four individuals here. So, and what it does is that we for it to we can use it for object tracking. So this can be used for tracking. And one thing there is that it can we can use computer vision, can utilize it, the algorithm to predict future actions or events. And one thing there is this is we can also use it to extract info and discover pattern. Now, in this case here, we can see here, just merely looking at these two people here, we can say, okay, that they are couples with the way they are holding their hands, just the prediction that we have here. So, we can train a computer vision algorithm model whereby it will be able to identify couples. That is, if they are holding hands. That's one thing that we can do. So computer vision helps in classification and discovery of pattern. So now, what computer vision can do is this. Now, there are some established computer vision tasks that can be done or carried out. Number one is object tracking. Number two is image classification. Three is content-based image retrieval. And four is object detection. Now, for the object tracking, we can track an object after detecting it in an image. So, for example, Let's say we are trying to track a criminal, or maybe we want to track unusual activities in a store or in a mall. We can use object tracking to achieve that. And also, we have image classification as predicting which class does an image belong, which is very common in a lot of computer vision projects. And also, we have the content based image retrieval, which means searching and retrieving images from data sources based on some certain features. And also, another one is the object detection, which also is very common when it comes to computer vision projects to detect whether an object exists in an image. That's to detect, that's object detection. Now, if we talk about image classification, what it does is to classify this particular image. What class does it fall under? Okay, for example, here we have a label here, which is this is a rabbit. Classify this as a rabbit. We have classification of animals. These are animals here. We have rabbit, we have dog, and we have cat. Yes, so which is the label. So image classification is one of the things that is generic to computer vision. Now, another thing is object detection. Yeah, in this case here, we can actually create bounding boxes, which I'll still show us how to use some annotation tool, whereby when you use the annotation tool, it creates different classes, color of classes, and we can have each color corresponding to a particular class. That okay, a purple color is used to identify someone that is a human being, a person, and the yellow is for the car, the red is for the cat, and while the light blue is for the dog, and the light green is for the dog. So which is being shown here. So all this what object detection is about. Yeah, to detect if something, if an object is in a picture or in a video. So that's one thing. So another one is object tracking. Object tracking in the sense that we can track an object, we can track a face, we can track a car based on when we actually see a license plate that actually hits what we want to track. So we can do that. You can use that to track, or we can track a particular model of a car or a particular person based on facial expression of the person. We can track someone. So another one is image retrieval. So now the query is this: we can query a database. So where we use computer vision. So we want to query an elephant, then it goes through a content, and then it actually fetches the one that looks like the actual query that we want. So which is an elephant. So it returns. So the query goes in, it looks for which one matches this exact feature, the image that matches this, and it returns the one that looks like it. So now we can talk about some applications of computer vision in autonomous vehicles. Number one is vehicle detection, which is shown here. And number two is pedestrian detection. And number three is traffic sign recognition. And number four is lane markers detection. So now all these things are the things that are peculiar in a working environment, or in a country that have a working transportation network and system. All these things has to be in place: vehicle detection, pedestrian detection, traffic sign recognition, lane markers. All these things must be there so that an autonomous vehicle will be able to detect all these things and act based on them. So like the traffic signs. So an autonomous vehicle should be able to actually identify, okay, when okay this sign is red, okay this yellow, which and green can go, and be able to identify if pedestrians are crossing, so the car won't drive and hit a pedestrian. So that's one application of computer vision. Another one is in face recognition to identify a face. So and one thing there is the NEC face recognition technology is the world best in search speed and accuracy when it comes to identifying a face. So now we can create, for example, now it's much more easier if, let us put it this way, the police department, or let's say NPF, Nigerian Police Force, have a system whereby we have all the offices of almost all the whole Nigerian populations in their database. whereby we can be able to track someone to recognize a face when it hits up or comes up in a mall or in a public place. So we can be able to identify the person. That's that one. So an application is face recognition. So also we have robotics. So computer vision and robotics. For example, there are some certain or complex uh, procedures. That's even in medicine a lot or in industry, whereby in manufacturing industry we can actually program computers whereby they have the capability of using computer visions to carry out some tasks that are very tedious or hard. So we can use computer vision for that, can program it. And most especially in the industry, that's where application of computer vision is. In steel industry to detect fracture or cracks in steels, that's computer vision, that's application. So in the food industry and a lot of things like that, and so on and so forth. So it has more application in the industry. So another one is Google Translate. That is, you can see what is on this image is written in French, access à la ville. So, and if you look at it, when we use Google Translate that uses computer vision, it can be able to translate other language into English. So when you put it, you are not seeing the sign that is here. You are going to see um, the translation in English. If someone does not have first-hand knowledge of what French is. So you can use this Google Translate. That's another application. Another application is in mobile computing, whereby we can actually use that. Maybe, for example, if we want to actually, a lot of people that do use this mobile computing are people that are into those that actually design a house or furnish a house. For example, you can see the person that is holding this phone here is trying to see if a chair can fit in this corner like this. So that's what it's trying. So that the computer vision can actually bring in an object to actually fit a particular space if it looks okay or it makes sense. So there are a lot of use cases like that where that can be used. Another one is in the airport or in any station. For example, this is a train station. You can see if someone abandoned their luggage or baggages, then we can actually create a computer vision system that can actually detect that. So as you come down from the train or you come down or you're in the airport or anywhere and the computer vision system has actually seen that you are the one holding that bag. So anytime you actually move far away from the bag, so it's going to actually trigger particular let's say it's going to notify the people in the control room, okay, this so person has moved away from his bag, or it can be used to identify if someone wants to drop a bomb or plant a bomb. So a lot of use cases like that. That's numerous application. Another one is in medicine. That's where computer vision also have a lot of usefulness, where we can use it to detect brain tumor as brain tumor, or if can detect any form of abnormalities in the system, so in the lungs or in the heart or in any part of the body. Now, let us talk about feature extraction. Now, what is feature extraction? It has to just do with extracting the features that are actually going to be useful during the training process of the model. And one thing there is that how do computers understand digital images? If you want to train images, now how do computer understand them? How do they how is it that an image is being transformed into something that a computer can understand and then train it, and then you now bring an unlabeled image or something unseen data, and you pass it into the model and it will identify that image correctly. So how does that happen? So when we talk about digital images, one thing there is that representations of real image has a set of numbers. That's the point. One thing we should know, that there are zeros and ones and they are just numbers. And they can be divided into small areas, which are called pixels. pixels. And pixels hold a small set of numbers for color, for brightness, intensity of light. That's what we should know. So that's one thing that is generic to digital images. So still on how the computers understand digital images. Now, there are types of digital images. We have three. We have the binary, we have the grayscale, and we have the color. So these are the types of digital images. And a computer can understand these three depending on the type of task we want to do. So still on how the computers understand digital images. Now, we talked about binary, grayscale, and color. I want to talk about binary. What is binary image? A binary image is an image that is just what zeros and ones. So it's just going to be able to, for example, you can see this particular pixel here on this image. This is the representation of the binary image in zeros and one. So that's binary. Now, we will now move to grayscale image. A grayscale image still for the same pixel on that image. You can see that it's giving a different combinations of numbers. So it's a grayscale is different from binary, and then the one for color. So the one for color is also different, which is given in this format. So a color image is RGB, which shows the red, green, and blue. So that's for color images, which is RGB. So this is the way it is. And this, when you feed it into the computer, this is what the computer sees, not this. It just actually gives a representation of it using numbers. The same thing as the grayscale, same thing as the binary image as well. Now, still on the color image, like we said here, if you look at this, yeah, so it has, we said it has the RGB, so which is the red, the green, and blue, which is being combined here all together. But now breaking it down, we can see it that we have it this way. The red has its own representation, the green as well, and the blue. So they are different. So the combination of it is what can be written in this format here. So that's that on that. Now, still on feature extraction. What are features of an image? Now, when we talk about features of an image, what are the things that we need to consider? We visual parts or patterns in an image. An image has visual parts and it has patterns, and it is useful to identify it and extract information from it. So it's the information that are there that we want. So, and where do we find the features? They are always at the corners, the edges, the regions of interest, which is the ROL, the row points, and etc., depending on the feature we want to extract. Because in an image, it's not all the whole features that are important. For example, if it's just if you snap yourself and you want to do facial recognition, it's just your face. So that's the feature we want. So we won't consider other features. So the features that are important are the corners, the edges, and the region of interest, and any other point of interest. So now talking about the edges. Now, where to find these features? Now, if you look at this image that we see here, now we can see a lot of edges. We can see edges, we can see edges, we can see edges. There are a lot of edges here. So edges also has a lot to do when it comes to features that are important that we can consider where we want to train a computer vision model. And we also have corners. Now, for example, if you look at this image, the corners are marked with the star. You can see this. These are corners. You can see them. These are corners, these are corners, these are corners, as you can see. So there are a lot of corners in this image. So these are features that can actually help us to identify a lot of things in this image here. And another one is regions. So the regions, for example, if you look at this particular image here now, So you can see that the regions, you can see a lot of region. You have this here. This region is different from this region. It's different from this region, and it's different from this region based on the feature of the image. And same thing goes for this one and this one as well. So now still on feature extraction, looking for features using the pixel representation. That's one way of looking for features. We can use the pixel representation, and we have the low level features and we have the high level features. So, and those are the hierarchy of features that we have. We have the low level and high level. What do we call low level features? It has to do with capturing local appearance or texture statistics of objects, and it is highly effective in classification task. When we want to classify something, we use the low-level features. That's one thing we need to consider. And for low-level features, the algorithms are the SIFT, the SOF, and etc. We have the interest points, we have the edges, we have the corners, etc. So that's for the low-level feature. Now, for the high-level features, we have semantic concepts that can be interpreted in a scene. And we also have the probability of observing an object in an image. That's for the high level feature. So, but most especially when you want to talk about classification problem, and so we use the low level features. And for the high level features, is mainly used in computer visions. And an example of that is birds, leaves for the high level features. You can see this. So these are high level features to consider in this image, here. So these are high level features. Now, before I move into what is deep learning and how images are converted into a neural network, and what happens during the training and everything using a convolution and convolutional neural network. So I don't know if there's any question so far before I move forward. Hello, do I have any question?
Any question, please? Are you done with these aspects? Okay, please, you can
I want to move into another aspect.
move on to deep learning, please. No question. If there is,
Okay.
they will raise their hands.
So we want to talk about what is deep learning now. So um, when we are looking for features using the pixel representation, uh, looking at the low level and the high level features, and when we talk about this is what they call pixel based. It just has to do with this is a low level feature. These are pixels, and for the object based, we have is actually classified as the high level feature. So, and a low level feature can translate into a high level feature depending on what we want to do. So, but the low level and for the low level and high level features, we can recall from the session on introduction to neural network where we had this image here for the low level features, which has to do with edges and dark spots. So that's for low level feature. For the mid level features, we have the eyes, we have the ears, we have the nose. Those are mid-level features. And for the high-level features, that's for the facial structure. So different type of faces. Those are high-level features because we can't integrate them together. My face is different from your face, it's different from any other person's face, except we are twin and we bear a high level of resemblance. And even at that, there can still be a distinctive feature, even for twins that bear that resembles each other to a certain level. So that we classify the facial structure as a high level feature. The mid level are the eyes, nose, ears. The low level features are the edges and dark spots. So let's move on. And what are the high level features that classify this image here? Now, for a car, what are the high level features for a car? What are the high level features for a human face? And what are the high level feature for a cat? Now, for a car, the high level feature is the tire and the headlight. So, if we want to actually be able to classify a car, we need to look for some things in the car. There's the tires and the what? the headlamps. So the
Okay.
headlights. So those are important things in the car, and you can even the side mirror.
Yeah, that's
Let's
a good
say
one.
side mirror, the boot, some other features. But a very high level feature is the tire
Oh,
for a car
oh
and the
yeah,
headlights.
more
And for the
important
human
than other.
face, a high level feature for a human face is
The other. The where is
the
it?
ears,
It's a
the
book.
eyes, the nose, and the mouth. Because normally, for us to actually classify something as a human face, then we must have all these things on it. The ears, the eyes, nose, and mouth must be there. So when we don't have such thing, either the person has a deformity or maybe an accident, and actually causes the feature not to be there. But the normal human face, all these high level features has to be there. Same thing goes for the cat, where we have the ears, we have the eye, and the nose and the mouth together, just the way it is indicated here. So these are what they call high level features as regarding to these three images here: a car, a human face, and a cat. Now, what are the high level
Yeah,
features that classify
what
this image? The
for
one
this
for
let's
this and the one for this. We have playing football and playing basketball. Now, there's something they call gesture or posture recognition. So now for this year, it is the pose of Cristiano Ronaldo here that actually shows that this is someone playing football. This is posture or gesture. So, and as well, we also have the ball, the football there. So also is part of the high level feature that classify this image uh, as playing football. And here also for the basketball, we have the player, the way they actually always stretch their hand, the way they pose while playing, and the basketball itself also is a high level feature to classify this image as okay that it's people are playing basketball here. Now, there's something that we must know about feature extraction. There are some challenges, and these are things that can actually affect the model performance while it's doing training and validation. One thing is called occlusion. Occlusion, we have illumination, we have scale, we have viewpoint, we have background clutter, we have deformation, and we have intra-class variation. So now, what is occlusion? This is occlusion. Occlusion means obstruction, something blocking the actual feature that you want to capture, the image. So, and it's not trying to allow you be able to say, okay, this is a cat or not. Okay, so and another one is illumination. Now, the illumination aspect is for this. You can see it here. So when there is too much light or exposure of that image to a light, for example, if a photographer is we go to for an outing or we go to normal Nigerian party where we have all these wait and get people that take photographers that do wait and get. If you see sometimes when they are snapping and they say, okay, do you like this? And you say, no, 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 it's too bright. So that's illumination, too much light facing the image or flooding the image. And that will not allow us to actually be able to extract features that we need. Another one is scale. Yeah, the scale is this. Now, for example, scale means that when we can't actually be able to see the whole object itself, like the viewpoint is too close,
what if when it's not
just
there?
too close. So, for example, there are some images that you take whereby you'll be thinking, okay, this can be a cat or this, and there won't be enough feature to extract in order to be able to use to identify, okay, this is a cat or not, or exactly if it is a cat. Another one is viewpoint. For example, how can we know that this is a cat? This viewpoint, we can use this type of thing and object recognition or image recognition of a cat, because there are a lot of animals that can pose this way that are even different from cats that we even think even say it's a dog or maybe another type of animal. Another one is the background clutter. as well. So the background clause is something that is at the background. That is at the background can also affect feature extraction. Another is the information. Information. So this is an example. The not properly shown should appear. And another intra-class means having type. This actually it's type of dog. If you look, you can easily say, okay, this is not a cat or maybe a dog. Because we have different animals that can appear. So now a cat the mission to we have see the string our model. Now let's move on. Now, what's the difference between classification and regression? Classification versus regression. Now, classification is predicting a label, and the outputs are discrete, and the output is always equals to the labels. That's for classification. And the input values can be continuous, keeps going. And use cases are forecasting the weather. So the classes where we can see under that is it sunny, is it raining, is it cloudy, or is it snowy? And that's for classification. And the one look at regression
We
actually
can't
has
see
to
your
do with
screen. We can't see your screen again.
Excuse me, sir. We can't see your screen, sir.
okay, let me can you see my screen now?
No, sir. No, sir.
Oh, sorry, I think the network.
Okay, sir. We can
Oh,
see
can
your
we all see
screen.
my screen now?
Yes,
Okay.
sir. Yes.
Yes, we can.
So I think where did it stop? Is it at this point before I move to? I think I was talking about this. I think I was done. This was what I was talking about:
We're talking about
classification versus regression.
yes. This is where you are.
Okay. So the classification we said is about predicting a label, and the use case is forecasting the weather, whether the and can actually the classes to consider as whether it is sunny, rainy, cloudy, or snowy. Based on we said that the input values are always continuous and the outputs are always labels. And labels in this case are like sunny, rainy, cloudy, and snowy. Now, for regression, it has to do with predicting a quantity. The outputs are continuous. And example of that is an integer or floating point value. And the outputs can be converted into labels to present a classification problem. And use case is predicting the value of a calf 2 years later. So now if you want to know the value of a calf 2 years later, we can do that. So using regression. So the graphical representation of that is this. This is classification and this is regression. So regression has to do with fitting a line. So that's classification versus regression. Now, still on classification and regression. Now, classification in computer vision. Now, what classification is this: when we have a cat, this is a feature here, and it's in pixel, a pixel representation of this image is given as this, because this is what the computer will understand. Computer cannot understand this, so computers only understand zeros and ones, numbers. So, and trying to now convert this pixel representation using classification. So anytime we want to predict a cat, we will need to actually look for this pixel representation. So, and this, we have some classes to compare with: cat, dog, and mouse. So now the probability that this is a cat based on this pixel representation of this input image is 0.85. And you can see the pixel and the probability for dog and mouse is actually lower. So which shows that no, that it is not, this input image is not a dog, this input image is not a mouse, but it is what? It is a cat. And it says unique features of a cat can be found there, which is the ear, the position of the ear, the eyes, and the nose and mouth. So that's one thing to note. That's for classification in computer vision. Now, for regression in computer vision, now if we take this input image and we turn into a pixel representation. Now, if you want to give a regression in computer vision, it actually has to do with trying to predict what is the age of this person, because that's one thing that regression can actually do for us. In this case, what is the age of this input image? So you can see it's telling us that 89.72% that this person in this image is 44 years old. That's what it's showing. That's for regression problem in computer vision. So which means regression can also find its way in computer vision. Now, going into convolution. Now, I won't even go into the mathematical aspect because I'm not interested in it. So we just explain what it actually looks like, and we just give the mathematical equation. So convolution is a mathematical operation on two functions, which is f and g, to produce a third one. Result is that it actually helps us identifying how f can modify the shape of g. That's what convolution is. And the definition is the integral is the amount of over f as it is shifted function g itself, which is shown as this. So we must have seen this before. This equation. So convolution. So those engineering must have seen this before. Those that did pure math must have seen this before. So convolution. So and this is the way it looks. So where we have function g, where it is moving, the function g is moving, and we have f. So when these two functions overlap, it gives an output, which is a third one, which is this representation that we are seeing here. So this is the output, and it's actually equivalent to the overlap of these two functions f and g when they convolute together. So still on convolution, we can have two different function f and using another function g that moves over this function f, and it gives us different output based on different function variation of f that is here. So which we can see in this graph that is being displayed here. So, and one thing we want to look at is how uh, we can apply convolution on images. How can we apply convolution on images? Now, for example, if you look at this, let us say this is an input image, and we know that input image are always represented as pixel. Input image is always represented as a pixel. Can we still see my screen?
Yes, yes.
Okay. So now this image is being represented as a pixel, and the input image, when we actually apply another function with it, which is we can call it a filter or a kernel or a mask, it can actually give us an output. That's what convolution is. So what we are trying to explain here, where we have, let us say G, in this case is the input image, and F is the mask or the kernel itself. Then when they mix together, it gives us an output. So that's what is happening here. For example, if you can see this particular, let's say this 3 by 3 feature that we actually highlighted here. You can see if it acts on this filter or mask, there's always an output that it will give us, output image it will give us, which is a feature map. And we're going to look at how it actually operates and how it works. I'm going to look at that, and we are going to complete it on our own, because there's a way it actually work. Now, one thing there is, if you look at this now, we want to talk about binary input image now, where we have zeros and one, and where we have the filter kernel mask also in binary as well. So Now, if you actually match this, convolute these two together, what is going to be the output? What's going to be the output that we are going to have? So that's one thing we need to look at, because this is the mode of operation when it comes to the way the CNN architecture operates. That's what happens, because there's always a convolution layer there that's going to act on the input image. So, and when it acts, it keeps passing it forward and forward inside the architecture, but we'll get there soon. So, now looking at this, what's going to be the output image or the feature map for this? So, we're going to look at that now. Now, if we look at this, just merely looking at this here, this is 3 by 3. Is that not it? So, now we have this input image here. So, but what we have here is we have the mask. This mask, we are going to put it on this pixel representation. So where we have it this way, we have this one is for this. So we are going to have 1 times 1. You can see, we have 1 times 1 is 1. So plus 0 times 0 is 0. We're going to have 1 times 1 is actually plus 1 as well. So we're going to have 1 times 0 is 0 plus 0. So we're going to have 1 times 1 is plus 1. As for this, 1 times 1 again is plus 1. 1 times 1 again is plus 1. I'm going to have 0 times 0, 0, and we have 1 times 1. So we have plus 0 and plus 1. So when we add it, 1, 2, 3, 4, 5, 6. So we are going to have our 6 here. So now the same thing again. We're going to use this as well again. We're going to use it on this. So this is the way it operates. Now let me explain this. So now we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we have 5 by 5 and we have 3 by 3 here. So now what is going to happen here is that the filter or kernel mask is going to also be the output of it. That's what it's going to give us. But we are actually trying to convolute on this pixel representation. So this one again is going to move here. So the first one is we moved on this. So the next one is you can see. So the next one here that actually operates with this mask is going to give us the output for this one here. And as well again, the third one, where we have this, this, and this, 3 by 3, is going to give us the output for this. Then we now move again. Since we are done with the top one here, we're going to move from here. You can see this, 3 by 3 is going to give us the output for this. Next one is going to be this up to this point. It's going to give us the output for this. And then the last one, this and this, will give us the output for this. So then the last one is going to be this. You are going to start from here. This for this is going to give us the output for this. I'm going to have this, this, and this is going to give us the output for this. And the last one, this, this, and this is going to give us the output for this. So that's the way we'll get it. So we use all this mask here and we'll put it on it and we calculate the value and it gives us the output. So we're going to see that because it has to do with shifting the filter around the image, the input image. The amount by which the filter shifts is called stride. In this example, we have stride is equals to 1 here, and which is this one here. The stride here is 1. So, and if we go ahead and try to calculate for the next one, like I said, which showed us here, which is going to be this 3, we're going to have it just this way. The answer is going to be 2. And there's a reason for that, why the answer is 2. So let's calculate that. So I'm going to have 0 times 1 is going to be 0, which is the 0 times this one. So then we are going to have 1 times 0. 1 times this 0 is going to be still 0. So we're going to have 0 times this one, which is shown here. It's going to be 0 as well. So we're going to have this next one. 1 times 0 is 0. It's going to be this. We have 1 times 1. This is going to be 1. Shown here. We have 0 times 1. That's 0 times this one. It's going to give us 0. We have 0 times 1. 0 as well. Again, we have 1 times 0, which is 0. And we have 1 times 1, which is 1. So now adding this together, we have 0 plus 0 plus 0 plus 0. We have 1 plus 0, which is 1, plus 0 plus 0, 1 plus 1, which is going to give us 2, which is this here. So now you can complete the rest by yourself, but the next value, the answer is going to be 3. Next one is going to be 4, 3, 4, 4, 4, 3. So that's the output using this mask on this pixel representation, which is binary. So now, what about this particular one for this here? So how do we calculate for this? You can see it here now. We have this one. The convolved feature is going to be the output after we use the mask. You can see, for example, here, the output for this is 4. And when we shift it again, as from here to this point.
Not less than 3 minutes for the class to end. And we are going to share on that link again to join.
Okay, so we have this as well, which is shown here. The output is 3. Then the next one is 4, just where we have it. You can see, so it keeps going on. This one is 2, this one is 4, this one is 3, and we can carry on and also carry out the rest. So that output is called the convolved feature itself. Now, still on applying convolution on images, because what we are interested in is the convolutional neural network. So let's say this is the input image. You can see this. So this is the input image, and we have this as the pixel representation. And for this, that's simple box blur, and we have simple. We have the horizontal lines. So that when we have let us say, for example, this convolution, this is what we use on this particular image, and it's going to give us this blur. So now using this image too on this mask, this feature, this mask, rather the kernel, if we apply it on this, it's going to give us these horizontal lines. So we can have different convolved image when we apply a mask onto a pixel representation. So the output for combining this input image with this is the simple box blur, and the one for the input image with this mask is the horizontal line. So having different convolution on different images is going to give us different outputs. So another one is this as well. You can see another combination. When we combine this and this, it gives us edge detection. And for this as well, it gives us the Laplacian operator. So for us to detect edge, so this for edge detection, this for Laplacian operator. And as well, we want to look at the reason why convolution is important. So we want to see the reason. Now, a simple case study is where we want to try and classify the letter X, even if it is rotated or shifted. So trying to identify or to classify the letter X. For example, here, the letter X in a binary image is this. For example, if let us say I wrote letter X here. So now how can I turn this my writing into a binary image? It is this way, it's very simple. So for me to turn into a binary, so just imagine I have let me say, okay, let me put it this way. I have max here. This is it. And Let me write another x here again. So now let us now put it in a box, and let us now group it. So um, depending on the features, the size, the pixel size we want, depending on that. Now, if you look at this, inside this box here, we have our feature. The feature we need is there. So we call it 1. So there's no, our feature is not here. We call it 0. So the feature we need here is 1. So now there's no feature here as well. The x is not overlapping here. We write 0. It's overlapping here. We put 1. So here we put 0. Here we put 1. Here we put 0. And here we put 1. So if I want to the pixel representation of my x, me writing my x is this. We have 1, 0, 1, 0, 1, 1, 0, 0, and 1. So I have it here. So that's just the way to give a pixel representation, or that's for binary. So I want to represent that as binary image. So this is it. So that's what is happening here. So where all these black spots are going to be 0, and the white spots can be called 1. So now let us try and move forward. So now one thing there is that we want to classify the letter X, whether it is rotated or shifted. So now if you look at this is letter X here. You can see this, and we can see this as well. This is the scaled version. So it is still the same feature. So it's the same feature. So the same feature that is here is the same feature that is here, even it was shifted. Somehow it was shifted or it was rotated, it's still the same feature. That's one thing why convolution is important. So now, one thing there is this, is that why is it important to use the convolution is that number one is, if even if there are some things that were like changed. For example, this one, if you look at this here, we have a feature that is here and a feature that is here. So, and if you look at it, this was shifted up, it was shifted up here, and this as well was shifted, it's not shifted, or it's just still in the same place as before. So it still captured it, and even if it is the scaled version, if you look at the way it goes, you can see it is still representing X, just the same way we have our X here. So this, even if this was rotated, it's still talking about the same feature. So, and looking at this, we have filter 1. Here we have filter 3. We have filter 2. So, and if we combine these different filters together, we can see that we still have the same letter that we are trying to classify. So that's one thing about convolution. So it actually helps us to, no matter how we change, or if pixel representation changes, it still keeps the feature intact. So now, talking about convolutional neural network, which is called CNN. So we want to look at what it is all about. So when we talk about fully connected neural network, it actually has to do with a network that is dense, it has numerous neural networks. So, and we have talked about that in the basics. And the first question is, can we use them for processing image inputs? That's the first question. One thing is that the regular neural networks do not scale well to full images. That's one thing. And we need many calculations and parameters. And also, we will lose the spatial information. And the reason is because There's something they call flattening. Flattening a 2D image into a 1D vector is not good, and it's going to actually allow us to lose the vital information of the feature we are trying to actually extract from a particular image. And the example is the nearness of pixels to each other. And we are going to talk, I'll share us a document, an article that actually talks about this losing spatial information when we talk about flattening in particular, flattening. So when we flatten an image, we actually lose a lot of information from it. So now, one thing there is this is that when we talk about a, a pixel representation, how do we preserve the spatial structure? That means the whole of the image. How do we preserve it, the features in it? And one thing there is connecting slices of the input instead of connecting all input values to neurons in the hidden layer. So it's not making sense to actually take everything and put it inside just one neuron or put it inside the whole neural network. We have to slice it, like take them into patches, like chunks. So each patch, which is called a slice, we have to put it to a single neuron in the next layer and so on and so forth. And this approach preserves the spatial information and the visual feature. And one thing there is that, like I said the other time, if you look at this feature with a mask or a kernel actually gives us this information. So onto the next one, it actually preserves it. And the same thing as well for this. It goes on and it goes on and it goes on. So it's just like it's simply a sliding window can do the rest. So we just keep moving and sliding it to the next one. It gives us the next one, the next one, the next one, like that, like that. So now, one thing there is this is that um, we have what they call filtration plus shift, extracting local features, then extracting different features needs several filters. And that's where what convolution is all about. Where we want to extract different features that need several filters, we need a convolution so that we can keep the spatial structure of the features we are trying to extract. And what is a convolutional neural network? Convolutional neural network, also called CovNets, it utilizes the mathematical foundation of convolution for computer vision tasks. That's what it use, and it is inspired by the organization of the visual cortex, and it has much lower preprocessing comparing to other classification algorithms, and CNNs can automatically learn the filters and characteristics of any feature. And the overall process in a CNN actually has to do with input image going inside. And one thing that happens is it's the CNN architecture learns the weights and the biases inside the feature, the input image, and it actually helps us to differentiate or in the differentiation of objects in the image. So that's what CNN is all about. Just simple, just this simple term. The image goes in, the CNN architecture learns the weight and biases and be able to differentiate what is inside the image and distinguish it from one another. Now, this is, we want to now go into what CNN is. We want to break it down. So, in contrast with the regular neural network, the layers of a convolutional neural network have neurons arranged in 3 dimensions. So the neurons are always arranged in 3 dimensions, where it has what I call the width, the height, and the depth, which is shown here in this case here. And note that the depth is the third dimension of an activation volume. And also take note that each layer converts a 3D input to a 3D output of neurons. That is for the activation functions. So we are going to see that. So whenever we have an input image, the image is being seen as imputed as image height, the image width, and the channels is seen as 3D, which is an RGB. So, and it goes into it the convolutional neural network, and whereby we have the width, depth, and height that is arranged in form of neurons. And we are going to look at this here. So I want us to go into the different links and read all these papers. And they are popular architectures of CNN, because CNN is very popular when it comes to computer vision projects. They are very, very popular. So, and we want to look at the rules of CNN. So, assuming that the inputs are images, so it gives us more efficient network, and reducing images into a form that is easier for processing, and it also preserves the critical features of images for prediction and reduces the complexity of the image classification task. So the popular architectures are AlexNet, the LearNet, the Google LearNet, the ResNet, and the VGGNet. The one that is most used basically for the CNN, most used is the ResNet. Most especially is the ResNet. It's very used, and followed by the VGGNet. So well, these two are used more often. So we can go and read. These are papers and publications that actually breaks everything down very well when it comes to the different types of architectures of CNN. So you will find it very intriguing to read. We want to actually understand CNN properly very well. So now this is what convolutional neural network looks like. So it utilizes mathematical foundation of convolution for computer vision task, like we said, and we always have a room for input, and where we have the convolution plus the ReLU, which is the convolution function, and the activation function, which is ReLU. So CNN uses ReLU for all the old hidden layers. So that's what it uses. That's the activation function that is popular with CNN, ReLU, and it has a pooling also, where it can be able to pull the feature after the input image has been actually convoluted with the activation function. So the pooling function, and there's also another layer again of convolution and an activation function again, and there's also another pooling, and whereby we now flatten it, and then we get our result. So we'll look at it very well. So there are some layers, CNN layers. We have the convolution layer, we have the pooling layer. And the pooling and the convolution layer is what is called the fully connected layer. So, and one thing there is that convolution layer, where the kernel is, which is called a kernel itself, the output is always given as a feature map. And one thing there is that it actually helps us to extract high-level features. Examples are the edges, and also it helps us specifying the characteristics of the kernel, including the kernel size, stride, and padding. So one thing there is that if we are trying to applying the kernel and ensuring that it is transversed, and the entire image, transverse the entire image. For example, if you look at this image, input image, which is this blue, we have the RGB, so which shows the image width, height, and the depth as well. So it's being changed. The kernel with 12 filters is going to change it, because, like we said, the CNN is a 3D that has neurons in the height, the depth, and the width. So we have it just here, whereby we're going to have 12 filters. That's going to, that means different filters just at the hidden layers, so which are going to be built around the input image in terms of the the dimensions of the input value for the image, the pixel representation. So now, one thing there is this is that
Hello, everyone.
we then try to add a supplementary step to the convolution operation, so which is the activation function, which is often ReLU, which has to do with replacing negative values by zero. So that's what ReLU does. So the input value is always going to be for ReLU, tries to turn any negative value turns it to 0, and the other ones can be any other value. So we should note that the rectified linear unit is not a separate component of the convolution neural network process. So they are together. They are always together. So we also have the pooling. So the pooling layer, which has to do with downsampling. So the output is always a pooled feature map. Like I said, when we have the convolution and the ReLU activation function as worked together, this pooling is just a map. It pulls out whatever it is happening here, so that the convolution and the ReLU, so together with the input features, it actually convolutes it, and with the addition of the ReLU activation function, then the output is a feature map, which the pooling actually helps us to bring it out. So with a convolution layer, we can form a layer in a CNN, and it actually helps in reducing the spatial size of the convolved feature. So that's one thing about the pooling layer, and it decreases the dimensionality and computation. So for the CNN architecture, and there are two types of pooling that we have. We have the max pooling and we have the average pooling. So the max pooling returns the maximum value, and it is recommended due to the noising advantage. And max pooling is much more used, basically, other than average pooling. And we also have average pooling, which returns the average of all the values. For example, in this case, here, this is max pooling. Here, the max pooling here actually returns the maximum value per this thing. So for example here, if you look at this here, let me use this as an illustration. If you look at this here, we look at this. If you look at this, and we look at this, this will definitely give us the maximum here feature. The maximum value here is 234, which will give us the first input here, and the maximum here is 97, which we can see here, and the maximum here is 203, and while the maximum here is 102, which we can see, which is here. But for the average, we take the average of these four, and the value is going to be 113. The average of this four is going to be 61. The average of this is going to be 137, and the average of this is going to be 54. As for the average pooling, so that's what the pooling layer does. So actually helps us to decrease the dimensionality. So now the pooling layer, this is what it does, like we said. So if you look at this, this is 48 times 48 times 3. So if the input image goes into the kernel itself at the convolution, then we have it this way, 48 by 48, where we have 12 filters. And these 12 filters actually, after everything has happened here, so it's being downsized and reduced. So, and reduced to 24, 24, and 12, just the way we can see, which means it's still retaining the number of filters that are here. So now in this case here, we can see that the pooling layer actually helps us reduce or downsample the feature map, so that we won't have ambiguity or the values are going to be too big. So it actually helps us to reduce it. So which is what we actually explained here. So that's what is happening here. So, and we have what I call the fully connected layer, where we have the output. It actually has to do with the mapped class cores, and has to do with optimizing and computing class cores. And we should know that the input of this layer should be flattened, and also the output can be normalized using softmax algorithm. So, and each neuron is connected to all nodes in the previous step and generally found at the final layers of the CNN. That's for the fully connected layer, which is the FC. So, and the at some point they can be used along with ReLU layers. And the last fully connected layer is the output layer. So this is what we are talking about. That after the input image and the convolution itself and pooling, so we also have another convolution plus ReLU here, and we have another pooling. You can see it's reducing it. So then we have flattening. So where we flatten the feature map, the output feature map, then we have the fully connected layer where it gives us the final output. So this is what a CNN is all about, and we can see that here. So this is just what it is. We have the input, the convolution, and the ReLU together multiplied by the number of kernel or mask. Then we have the pooling. The pooling occurs then multiplied by another number of mask as well. Then we now have the fully connected layer, which can be used with a ReLU function with a particular number of masks again as well. Then we now have the final output, which is the fully connected layer. So this is just what simple mathematical or algorithmic expression for the convolutional neural network. So this is just what it looks like. Yeah, and this image is a very popular image that we might have seen this almost anywhere. So this is what the CNN actually does for image classification. Let's say we have input images and we have extracted some features from it. So that feature is passed into the convolution plus ReLU, so which is this here. And this shows the depth. The depth shows the number of filters. The depth shows the number of filters that we are trying to use here in this convolution and ReLU. So, and we have the pooling as well. The pooling, the features here are moved into the pooling also. And from there again, we have another layer again, which is convolution and ReLU together. And we also have another pooling. So it can keep going and going and going like that till it gets to the output. So now the last part is where we have the flatten. So the output, the feature map, we flatten it. And after flattening it, you can use the fully connected layer is going to be the output. And we can still use some other things on it, like the softmax. Then the classification is going to come out, whereby we can say that, okay, this is actually a car. So, and this is not a truck, nor is it a van. So that's one thing. So, which is good for classification problem for the CNN. So, the way it works is also this flattening actually helps us to take the image into a column vector. That's what it does. Yeah. So the image goes into a column vector. That's what flattening does. It turns a 2D image or 2D feature into a 1D feature. So in an understandable way, but still keeps the informations that we need as well. And this is the last part where the squashes class calls and calculate the probability for each class of the features or the whole input that we have used to train the model itself. So CNN is used for classification problem, used for object detection, and used for segmentation. That's what it's mostly used for. And most of the computer vision projects we will do, classes we will do, or when we get to the practical aspect, we will be using CNN most often for classification, object, and segmentation. So this here is also for vehicle classification. This is just an explanation where we have the input image, we have convolution plus ReLU pooling. So we can have different number of layers. This a layer, this is another layer, and the pooling, a layer, another layer, pooling. We have a layer, another layer again, pooling. Then before we have the fully connected layer where it gives us the output that this is definitely a car. So not a truck. It shows lower percentage that is a truck, airplane, ship, and us. So that's classification that we did, the practical aspect we did inside Google Colab. This is just the way we use CNN. So this is what is happening in the CNN. Yeah, we have the input, yeah, and we have a kernel whereby convolution, which is convolution one. We have second convolution as well, and which is 5 by 5 kernel. So the number of channels, each channel is 24 by 24 times n1. So as number of layers that we have there. So the max pooling as well. So this is just the way everything looks like, and we actually get our output where we can have a prediction as 0, 1, 2 up to 9, since we are dealing with digits. So for image classification as well, also this is just the way it is. We have convolution pooling, the fully connected layer, and the output where it has the prediction as well. So these are some references and link where we can go and read some things. But basically, I want us to go and read a lot of things. I think this particular thing I talked about this. Okay. This is very important. It has this link to this type of, is very, very rich. So, and they have their use cases. So, but basically, most of the time, this is used more often, and this as well is used more often, so other than the rest. So, if we have any question, so can ask our question.
Any question, please? Audience, any question, please? Okay, if there is no question, that's okay. Mr. Ajayi, please, your question.
Good evening, sir.
You're welcome, sir.
I just want to ask, when are we going to start the coding aspects of deep learning?
On Thursday.
Okay. All right. Thank you.
Okay, sir.
Any other question, please? Okay, if there's no question, at this junction, I think we can round up and try to finalize the whole matter. So thank you very much for being part of this training from the beginning to this time. Thank you. The tutor, we appreciate you also. Thank you for your time. God bless you all. Thank you and good night.